Okay, good morning. And before we start our lecture of today, there is an announcement. Next week, I will not be here. I'm traveling, so we will not have in-class lectures. I will try to, I'm not promising, but I will try to record the lectures and put them on provide you the link, YouTube links, so you can watch them if I'm able to record them. One thing. Second, according to the tentative schedule, we were supposed to have our midterm 2 exam next week, but since I'm traveling, so we are postponing it by 1 week. So in next week, for sure, I will release a sample midterm 2 exam. And the syllabus, the material that will be covered for midterm 2 exam will be chapter 5 and chapter 6, only 2 chapters, okay? So we have already covered from chapter 1 to 4 in midterm 1, right? So you will be responsible for 5 and 6. But the final exam will cover everything. Okay. So any questions? Yeah.
We'll be moving the exam basically 2 weeks from now on another Monday. Next Monday then?
So next Monday is November 4, right?
Yeah.
It's not November 4, but the following one. Okay. Any question from the previous lecture? I know it was short, but if you have questions from the last lecture or the last week. Okay, if not, then we can start our today's lecture. We are still talking about process synchronization. Just to give you a background, in the previous lecture, we were talking about scheduling multiple processes, but then the question arises if multiple processes are sharing the data and we don't want to end up in a race condition. I already explained what was race condition. Hopefully you by now you know what is the race condition. So if we don't want to end up in the race conditions, then we need to synchronize the processes. The access of the processes to the shared data need to be synchronized. How we can do that? So we were looking at different solutions to achieve the synchronization. One of that was the Peterson's solution or Peterson's algorithm. We said that yes, it works, but not on the modern systems. And the reason for that was that the instructions are reordered by the compiler, and even the underlying our hardware or the architecture, it executes the instructions out of order to achieve the performance optimization. But as a result, the mutual exclusion achieved by which we were able to achieve using Peterson algorithm is not achievable anymore. Okay, and for that we diagnosed that reason was the reordering of the instructions, and we said, okay, how can we solve the problem? If we tell the processor don't reorder the instructions, if we put the barrier at appropriate points. And then for putting barrier, there are specific instructions which we can use. Like I didn't mention them, but there are instructions like sfence. S stands for store fence, or load fence, L fence or load fence, or memory fence. So mean the barrier, if you remember, we said that barrier, if you put the barrier, we don't allow the reordering of the instructions across the barrier, right? Now, the general type of barrier is memory barrier, where we said that all type of memory instructions are those which are storing the data or which are loading the data from the memory. So when we put the memory barrier, we say that all type of the memory instructions are not allowed to be reordered across the barriers, which basically means that all the stores and load instructions before the barrier must be completed before we can execute any store or load instruction after the barrier, right? But this is too restrictive. Too restrictive mean because we are restricting both type of instructions, store instructions and the load instructions. We are restricting from reordering. To relax the restriction, depending upon your requirement, you can either use the load barrier or the store barrier. So as clear from the name, if you put a load barrier, it restricts the reordering of only load instruction across the barrier. And if you use the store barrier, it restricts the reordering of only store instructions across the barrier. We didn't talk about that, but I just wanted to mention it. Okay. So we went through all this slide to understand what is wrong with Peterson algorithm and why it is wrong and how we can solve it by using the memory barrier instructions. Okay, so what we want is that if we want two processes or multiple processes to access the same data or which are like accessing the same critical section, and we want to achieve the mutual exclusion between those processes, ideally what we want is this kind of approach where we initially each process first must access a lock or acquire a lock. And once it acquires a lock successfully, then it can enter the critical section. And after it is done with the execution of critical section, it releases the lock so that other processes can enter the critical section. And then after releasing, it can do remainder section. Remainder section is one which is not, which doesn't share data with other processes. Okay. So, but here the point is that the assumption is that only one process can acquire a lock at a time. No more than one process can acquire a lock at any one time. Okay. This is like the semantic, ideally what we want to do. So one way to achieve this is what I showed you in the last lecture. One way to achieve this is that how we implement that lock is that acquire lock, we can replace it by using this simple while loop where lock is a global variable which is shared among multiple threads or multiple processes. And then each thread first keeps waiting on the loop while lock is equal to 1. So if it is 1, it means someone has already acquired the lock. So you cannot enter, you cannot proceed, so you must wait. So when someone sets the lock equal to 0, only then this condition becomes false and your control falls down. And then you set the lock equal to 1 and you enter the critical section. Once you are done, you set the lock back to 0, right? But then we said that this code is not correct. Why it is not correct? Because here we are writing the code in a higher level language, which is like, let's say C. And we are writing this while statement. But when you translate it into, so our assumption is that only one process or one thread can execute this statement at a given time. And our assumption is that this translates into a single instruction, but this is not the case. It doesn't translate into a single assembly level instruction. It translates into multiple instructions. And since it translates into multiple instructions, let's say it translates, I'm just building up a fake example. Let's say it translates into 10 assembly instructions. And those 10 assembly instructions collectively achieve this semantic, right? Let's say I am thread 1 and I have executed 5 of those instructions, and then the scheduler kicks me out. And another thread comes in, and then it continues. And as a result, what happened that both thread 1 and thread 2, they can enter the critical section. So to make it more clear, okay. So we have this while statement, right, which is implemented by both, by all the threads. In this example, we have only threads. Okay. So when I translate it to assembly, it looks like something like this. Let's say load into register 1 the value from memory address lock, right? And then let's say I'm giving it a label. I assume you know assembly language. And the next instruction is branch not 0, register 1, test. So here basically I'm saying that load the value of the lock in the register 1, and then check the value. If the value of the register 1 is not 0, which means someone has already set it the lock equal to 1, then go back and test again, right? But if it is 0, then store. So I don't remember whether we have the source first or the operand first, but anyway, I'm assuming that we have the destination first. So which basically means put 1 in the log in this configuration. Okay, clear? So you are on with me on this, that actually this 3 lines of assembly will implement this one statement, right? So this is thread 1, let's say, and here is thread 2. Now let's say we execute first this thread. Let's say we have a single core, so we can execute only one core at a time, one thread at a time. So let's say it reads the value of log. So here, let's say this is memory. Here we have log. The value of log is, let's say, 0. So it loads the value of log into register 1. So R1 is equal to 0. Branch not 0. This is false, right? So R1 is 0, which means that the next instruction that will be executed by this thread is this one, right? It will not jump back. There will be no loop. But let's say that before it is executed, before the next instruction is executed, here a context switch happens. A context switch happens, and as a result, this thread 1 is thrown out, which basically means that it is put into the waiting queue, and the thread 2 starts executing. So thread 2 also basically have the same code, right? So let's say it is doing load from the lock. Let's say I'm using another different register in register 2, right? So it reads the value, and in R2, I also get the value which is equal to 0, right? And then I say branch not 0, register 2, test. It has its own test table. So, but this condition is false, right? So I reach here, store, and lock. So I set this equal to 1, sorry. I set this equal to 1, right? And I enter my critical section, right? And let's say while I'm in critical section, I'm kicked out. And then this thread is again scheduled for execution. So its execution will start from this point, right? From here. So what it will do, it will also again write 1 in the log. So basically you are again having a 1, and it will also enter into its critical section. So we have both of them in the critical section, right? Which we don't want. There is no mutual exclusion there. So the problem is that this code will not achieve the mutual exclusion, and the problem is with the lock variable itself, because there is a race condition, right? We are not able, the issue is that we are assuming here that we are able to read the lock variable in an atomic way and then set it, but that is not possible. So the source, what is the source of the problem? The source of the problem is that if we somehow, we need to maintain that this while loop, which we were basically using, we were trying to use for mutual exclusion, we need to ensure that it is executed in an atomic way. So if I'm executing this one, no one should be able to interrupt me. I should not be scheduler or any other reason should not be sufficient for me to be kicked out. Okay. So which means that I need to read the data from the memory location, step 1, then test it, step 2, and then set that data. Step 3, I need to do all these 3 steps in a single step. Loading, testing, setting. Okay. So, but that we cannot do that. We cannot do these 3 steps in a single step or in an atomic way without the support provided by the hardware, right? So which basically means that we need the hardware instructions which do all these 3 steps: loading the data, testing the data, and then setting the data in a single instruction. We need special instructions for that. Okay. So we will look at, here it says three, here it says we will look at three forms of the hardware support, but actually I think it is two, because we are going to talk about test and set instruction and comparison and swap instruction. Both of them fall under this category. Okay, but I mean, if you want, you can say there are three different ways. Okay, so let me read this slide to make sure I'm not skipping anything. So many systems provide hardware support for implementing the critical section code. We talked about that we need the hardware support for that, and many modern systems provide the hardware instructions to do all these three steps in a single step. Okay, if we don't want to do that, let's say we do, then one other way is that on the uniprocessors, what we can do is that we can disable the interrupts, which basically mean that if the thread 1 is executing, before starting the execution of thread 1, I disable the interrupts, which means that I ask that don't allow any other process to interrupt my execution due to any reason. And once I have completed, then I will enable the interrupts. But then this is very expensive in terms of performance, because every time you have to, before entering, you have to disable the interrupt. When you are leaving, you need to disable the interrupt, and it also reduces the responsiveness of the system, because other processes, they must wait for you to complete your operation. Okay. So that's why we are going to have a look at the hardware support to achieve the atomicity of these three operations. So basically, one of them we have already seen, and I think you have used it in your project 3, which is compare and swap. The other is the test and set instruction. So these are special hardware instructions that allow us to either test and modify the content of a word, or to swap the content of the two words atomically in an uninterrupted way. So, okay, let's first go with test and set instruction. So test and set instruction, okay, maybe I can keep this as it is. Now let's say I have this lock variable, and its initial value is 0. Okay, so now what the test and set do is this. So what you want is that you want to test the current value of 0, and also to set its value, to set this memory location to a new value, but in a single set. Okay, so what you're doing is, yes, you can execute this test and set. So here you provide the, let's say, the address of the log and the value, the new value you want to set, and it will return you the old value. So here, basically, what you are doing is that if this instruction is executed, what will happen? That here this will be set equal to 1, right? And in this variable, you will get the old value, which was 0, right? So to understand the semantics of this instruction, you can have a look at this code. This is just to make you understand how it works. But the test and set itself is a single instruction. It is not a combination of instruction. Here we are just writing it in a high level language to make you understand how it works. Okay, the semantics of it. So test and set Boolean, a static type. You are giving the address of the memory location. Boolean is its type. So for example, in our case, it was lock. So you will give the address of the lock. So what this instruction will do is that, again, I'm emphasizing it that this is just, we are trying to explain how it works, but itself, test and set is a single instruction. Okay. So what it does is that it will get the current value of that memory location. For example, lock in our case, put it in RV, and then set that memory location to true. And then it returns the old value, which was RV, right? So what we are doing is that this test and set is executed atomically because it is a single instruction, and it returns the original value of the pass parameter. So the original value means the old value, which was already there in the memory. For example, in our case, it was 0. And then it sets the new value of the pass parameter to true. So it sets that memory location to true. Okay. How we can use it? to achieve the mutual exclusion. So now let's see. Now keep this in mind, right? We were trying to achieve this one while lock is equal to 1, then keep it, right? So we want to do the same thing. If anyone else has acquired the lock, we must wait, right? If no one has acquired the lock, we can continue. So here, what you are doing is that you are saying while test and set and lock. So here the same thing. You have, let's say the initially lock is equal to 0, so you are saying test and set lock. So what it will do is that it will set equal to 1, but it will return the old value, right? So old value is 0, condition becomes false, right? So condition becomes false, so it's mean you can enter your critical section, and once you are done, you set the lock back equal to 0, which is false, right? So now and keep this in mind that test and set is not only atomic instruction, there are two features. One, test and set is an atomic instruction. Second, only if you have a multi-core processor, only one core can execute test and set at a time. It is not possible for two cores to execute these instructions at the same time. If both of them try to execute this instruction, one of them will be blocked and the other will proceed. Clear? So does it solve our problem of critical section problem? We will see in the following slides. So in upcoming slides, that remember there were three properties of the mutual exclusion. Critical section: 1, mutual exclusion; 2nd, no deadlock; and third, no starvation. It achieves the mutual exclusion. It achieves the property of no deadlock, but it doesn't guarantee that there is no starvation. Okay. So for that, we need to improve our solution. We will see how, but it can achieve the two. It can at least achieve the mutual exclusion and no deadlock property. So we have made a little bit progress compared to the previous case where we were saying while lock is equal to 1. Okay. The other instruction is actually there are many instructions which you can use, which can do the same thing, like doing the 3 steps in a single step. Loading the value, memory value, then testing it or modifying it, and then storing it back. So test and set is like one of them. Like there are like test and increment and test and decrement. So you can go and check on Google. There are many various type of atomic instructions which you can use. So we are not going to cover all of them, but I just want to like give you the pointers here. So compare and swap, you have already used in your projects. Anyone who is not clear on this? Anyone who wants me to explain this? No? Okay. So then I'm not explaining it. So properties, it is also executed atomically, which basically means it performs the load operation, the modify operation, and the set operation of the data in a single instruction. Also, it returns the original value of the pass parameter here, compare and swap. It will always return you the original value. And it sets the value of the variable to the new value only if the old value is equal to expected value. Let me know if you want me to explain this. Yeah. Maybe I can keep the same example. So let's say you initially have lock. So what compare and swap does is that I'm just writing CS, compare and swap. Okay. So you provide the address of the lock. Okay. And what you want to do, you want to set the lock equal to 1 only when no one has already set equal to 1. Set the lock equal to 1. Okay. So you are saying, okay, check the address, the memory, check the value of this memory location. If it is equal to 0, then set it equal to new value, which is 1. Okay. And this will return you the old value. Okay. So what will happen is that this instruction will check the current value. If it is equal to 0, then it will set equal to 1. If it is not equal to 0, it will not set it equal to 1. But in all cases, whether this condition is true or not, which means basically the old value is equal to 0 or not, in all cases, it will return you the old value, right? So what you can do is like, you can test the value which is returned by this to implement your law. So if the returned value is, let's say, if the return value was equal to 0, right? So it's mean that if return value is equal to 0 here, it's basically mean old value is same as the expected value. So if old value is same as the expected value, it's mean you got the law, right? Because your condition is true, so this was set equal to 1. But if old value is here 1, which means already someone had set it equal to 1, so you don't get the law. Okay. So the semantic is like, this is how it, but again, this is a single instruction, but this is only the like kind of algorithm how it works. So you first get the old value in the temp variable, then you compare the current value of that memory location, you are dereferencing it with the expected value. If both are same, you set that memory location equal to new value and you return the temp, the old value. The old value is always returned, irrespective of whether your condition is true or false. Okay. So returns the original value of the past parameter value, set the variable value to the new value, but only if this condition is true. Okay. And how you can use it to achieve the mutual exclusion. So here is the example. Again, we have the same like infinite loop. Third, it will first execute this internal while statement, which is compare and swap and lock 0 equal to 1. So here basically what you are saying is, we are assuming by default initially lock is equal to 0. So what you are saying is that, okay, check if the value of this lock location in the memory is equal to 0, then set it equal to 1 and also return me the old value. So if the old value was 0, so then the loop will break. But if the old value was not 0, old value was 1, condition is true, and you will keep executing, right? Or keep executing the while loop. So you will not able to proceed. Okay. But if you get the lock, you proceed, you do your critical section. After that, set lock equal to 0 and do the remainder section. Any questions? Okay. Again, does it solve the critical section problem? This provides you mutual exclusion. This provides you no deadlock guarantee, but it doesn't provide you the guarantee of no starvation. So we actually, again, as I said, we need to improve our solution to achieve the guarantee of no starvation. Okay. So we will see how we can do that after the break. So I have a 10-minute break. You have a question?
Yeah. Does compare and swap also prevent other cores from using it to learn tests and stuff?
Yes, yeah, that's correct. So compare and swap can be executed only by one core at a given time in a multi-core processor.
Well, I think, no, I didn't, I think
Anytime I type about, then it's working. Anytime I type about, it just changes to a different. The next pause, you go right, syn, E, Y, and anything the language. Yeah, it's like all the organization over. Yeah, I sent the video. Sitting here.
But was very excited to be like that.
Yes.
Anyway. Yeah, we, so, probably,
Okay, so that has to last 3 days.
I know, you can. Well, you could, like,
No worry. I really think that we're having the running, there was burning. The communication with the city. I got it. What is that? I'm gonna have to.
Because. Yeah.
Yeah.
No, yeah, but you're fine, but
Yeah. Yeah, so yeah, we for yeah, I think the third week. The sixth. I think we actually was to give the positive. Yeah. Yeah. It's another $20. It's very short experience.
Yeah.
Maybe they can, but I'm sure.
Okay, so let's get back to the lecture. So we said that, okay, we can achieve the mutual exclusion using test and set or compare and swap. Actually, those instructions which do that load, test, and modify operations in a single step. But we cannot achieve the no starvation guarantee. So actually, this slide is saying the same thing. So just let me read it. So use of test and set and compare and swap as explained provides mutual exclusion. That is the first property is satisfied. First property of the critical section problem is satisfied. Progress is also satisfied, which means there is no deadlock, but bounded waiting property, third property, it may not be satisfied, which means there may be starvation. So, which basically mean that a process X, if you are using this one of these instructions to achieve the mutual exclusion, then it can happen that a process X may be waiting, but we can have the other processes Y going into the critical region repeatedly. Like for example, in our case, thread 1 is going into the critical region repeatedly, and thread 2 never gets the chance. So how we can avoid this? Okay, so it looks like bit complex code, but I can break it down for you. So here what we are doing is let's start from the top. So what you are doing is that you have an array with the name of waiting. So let's assume you have 4 processes, and we are naming those processes as process 0, process 1, process 2, and process 3, right? So we have an waiting array with 4 elements at index 0, 1, 2, and 3. So each one of those processes only sets the element of its corresponding index in the array equal to true. So like process 0 will set waiting 0 equal to true, and process 1 will set waiting 1 equal to true, right? And then key is also a global variable, which is shared among the threads. So all the threads, they initially set equal to 1, and then all the threads, they execute this while loop, the internal while statement, which says that while waiting, maybe I need to do it on the board so that if we have a fixed value of I, then it will be easy to understand. Otherwise, so key is a global variable which is shared among all the processes, the threads. So let's say key is initially equal to 0, and then weighting is an array which has 4 elements, let's say 0, 1, 2, 3, right? Process 0, process 1, 2, and process 3. Okay, so all the processes, they first set their corresponding entry is equal to true. So true, 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 and true. Okay, and then they set each one of them try to set key equal to 1. So depending upon, doesn't matter which one is the final writer, but the final value of the key will always be 1 because everyone is writing the same, right? And then they execute this while statement. So it's, what does this while statement say? This while statement says, actually, this is like you are trying to enter the critical section. Remember that we have different sections in the code of a process, like entry section, where you are trying to request the lock. Once you get it, then you enter the critical section. Once you are done with the critical section, you have the exit section where you are basically trying to reset the lock, and after that, you have the running section, right? So this is entry section where what you are doing is that each process is executing this while statement where what you're doing is that you are saying that you can enter the critical section only if the weighting, the corresponding element of the weighting is true and key is equal to 1, right? So let's say that all of them have executed their first statement. So for all of them, the while statement is true, right? Is it only me who's looking at the code? It looks like. So only for all of them, the while statement is true because all the elements of the weighting are true and key is equal to 1. But then in the body of the while, you have only single statement, which is compare and swap. And remember, we said that only one core can execute the compare and swap at a time. Let's say P1 gets the chance and all of the other are blocked. So if P1 gets the chance, lock is initially equal to 0. Lock is also a global variable. So it was initially equal to 0. So when you do compare and swap, okay, yes, expected value is 0. So set it equal to 1 and return the old value, which is put in the queue, in the key. So key is set equal to 0, right? So it's mean that process P1 enters the critical section and it also sets its weighting I equal to false. So which basically sets this equal to false, right? Now it enters the critical section, but before we proceed, since now key is set equal to 0, no other and all other like P0, P2, and P3, they fail to execute the compare and swap because as I said, only one of them can execute compare and swap. Let's say after P1, P0 gets the chance. But when P0 gets the chance, it says, okay, is the expected value equal to 0? No, expected value is actual value is equal to 0? No, it is equal to 1, right? Because we have already set equal to 1, right? So it will, what will happen is that once it failed, sorry for the mistake. So when P1 got the chance, P0 failed to execute, so it goes back into the while loop and it tries to again enter the while loop. So, but when it tests the condition of the while loop, now the condition of the while loop is weighting is equal to true, but and key is set equal to. So if it gets stuck here in compare and swap, the second, let's say the P0 gets stuck in compare and swap, then it tries again. So weighting is true. Weighting is true and key is equal to 0. So condition is false. Okay, I think I need to look again at this example. It looks like I am failing to understand it. But it looks like that. Yeah, I need to revisit and then I can cover in next slide. Okay, next lecture. But for the time being, we can skip it. But I will come back on it in the next lecture. Okay. So atomic variable. So we have seen in the previous set of slides, or like previous couple slides, that we can use the test and set statements and compare and swap statements to achieve the mutual exclusion. But the issue with them is, yes, they achieve the mutual exclusion. And even if, like the previous slide, which I was not able to explain, let's say if it is working correctly, we can even achieve no starvation. But still there is a problem. And that problem is the difficulty of programming, because these are low-level statements. So basically what happens is that a programmer have to very clear understanding of how test and set works and how compare and swap work, or all other similar type of instructions to successfully use them in the program. So what we can do is that we can use, in place of using them, we can use the atomic variables. So atomic variables, they are actually supported by the languages which you are using to write your code. So basically, just like, remember, different data has different types. Like, for example, you have a variable of integer type or Boolean type, a character type, and so on. So you can also add a qualifier to a variable with the name of atomic. Let's say if I write int x, so this is a regular variable, but if I put atomic here before it, so I'm saying basically that if I do any operation on this variable x, that operation will be atomic. Atomic in the sense, remember, we said if you want to increment x plus plus, so it translates into multiple assembly language instructions. So now we are giving the qualifier that when one thread is incrementing x, then no other thread should be able to increment the x. And underlying, like under the hood, how this atomicity is achieved is again through the test and set or a compare and swap instruction. But the advantage is that as a programmer, you don't need to deal with you don't need to program in terms of compare and swap and test and set. Okay, so instructions such as compare and swap, they are used as a building block for other synchronization tools such as atomic variable. For example, let's say you have a sequence variable, just like I gave you example in variable x, and you declare it to be an atomic variable. So you just put the atomic qualifier before when you declare it. Then any operation that will be performed on this atomic variable will be atomic in the nature, which means it cannot be interrupted. So how that is implemented under the hood, as I said, it again uses compare and swap. So let's say you perform an increment operation on that atomic variable sequence, then you will just execute this command, increment and sequence. But under the hood, what will be happening is this. Again, you don't need to worry about it, but because as a programmer, you will be just calling increment. So what this increment will be doing is that, let's say we use, or maybe we can use the same example. So let's say we have variable sequence, right? So now this time you will not say, you will say sequence plus plus, but how it will be implemented, this statement, how it will be implemented, it will be implemented by this code or this API where actually your compiler is taking care of this. So you will be doing sequence plus plus, and since you have qualified it by the atomic, so your compiler will know how to execute it. So here, what will you be doing? You are just having another temporary variable where you get the original value of the sequence. Let's say the original value of the sequence was 2. Okay. So in temp, you are just dereferencing it. So you get the value of 2. And then what you are saying is, okay, first give me the value of compare and execute this statement, compare and swap. So you are saying, is the expected value equal to 10? Yes. Expected value is same. So increment it and set it equal to 3 and give me back the old value. So 2 is not equal to 2. this is false. So which basically means this false statement will not be executed again, right? So what does it basically mean? It basically means this, that if here you get this value, old value in the temp, but before you are able to successfully, let's say, before you are able to execute this one, and other thread does the same thing, like it executes increment, right? And before thread 1 is able to execute this one, thread 2 is able to increment. So what happens is that the value which I will see after the other thread has implemented will not be 2. It will be the value that will be returned will be 3. So 2 is not equal to 3, condition is true. Again, I will try to implement. So I am trying to implement in an atomic way. I don't want, when I'm doing the increment operation, I don't want any other thread to come to interleave and update the value in between. The value I initially saw, which was 2, so it should be the same value which is returned. 2 is not equal to 2. So that's why I am able, my condition is false and I don't try it again, which basically means I have set my value to +1, whatever was old value +1. Any confusion or question? So the advantage, okay, here is the, again, I'm like stepping back a bit. We have seen test and set, we have seen compare and swap, but then why we even need these atomic qualifier or atomic variables? Because we want to save the programmer from the burden of dealing with low-level instructions like test and set and compare and swap. So what we do is that you can use the atomic variables, you can declare a variable to be atomic, and then the compiler will know how to atomically increment that variable. And you don't need to write your code in terms of including the compare and swap instruction or test and set. Okay. Okay. Let me go back to this slide here. Now remember, we have written this code using compare and swap, and we also had an example where we achieved the mutual exclusion using test and set, right? And again, here the problem is like, we are achieving the mutual exclusion, but you are writing the code by including compare and swap. What you can do is that to save the programmer from the burden of dealing with these instructions, you can put this code in a library function. And then all the time programmer only need to call those library functions. And if you do so, they are named as mutex locks. So what we can do is then we can put these entry and exit sections, which we have seen in the previous slides. We can put these exit entry and exit section codes into the lock and unlock functions in a library or a kernel. And then we have a lock implementation. So programmers just need to call those functions, and we call them as mutex locks. Applications will not be directly using hardware instructions, that is test and set or compare and swap or other similar instructions. Instead, lock implementation will use these hardware instructions within the body of those functions. So here is an example of lock implementation or mutex implementation. So let's say you first define, let's say you are defining this function and you put it in the library, and then the application you write it all, you include, when you compile it, you include that library at the compile time, and your application code only all the time call this function of the library. So in the library, what you are doing is you are first defining a structure. Let's say you are defining lock_t, and it has only one variable, which is flag. And then on the right side, you are first defining a function to initialize the lock. So you need to make sure that initially the lock is set equal to 0. Because in some, for example, in C, all the variables you define, they are initially set equal to 0, but in some languages they may not be. But you just want to be sure. Here, then we are defining two functions, one to get the lock and another to release the lock, lock unlock. So in the lock, what you are doing is inside the body you are using while test and set flag of lock. So we have seen how test and set will work. So it will set its value to true, but return the old value. If the old value was false and you set it to true, it means you get the lock. But if the old value was true and you set it to true, it means someone else had already set the lock, right? So you don't need to worry about this now. You can only call the lock function. For example, lock any variable x, let's say, okay, or any variable of this data type. And here, when you say unlock, you simply set the flag of that lock variable equal to 0. Any questions? Okay, so here is how you can use those library functions in your application code. So you are first defining a lock variable, lock underscore t, and you are naming it as a mutex. Then you first initialize it, init address of the mutex, and then which will set equal to 0. And then you are just simply calling lock the mutex. Then you will enter the critical section, and then you will unlock the mutex. So in here now you don't need to worry about test and set and compares. I don't need to read the statement. Okay. Now if we go back here, for example, let's say you have two threads, right? And both of them call lock. Both of them call lock, right? And one of them will get locked, right? Not both of them can get the lock at the same time because inside the body we are using the test and set. So the one which fails, one which succeeds is fine, but let's look at the thread which fails. The thread which fails, what it will be doing? It will be repeatedly executing this statement, right? While statement. So it means that it is doing nothing but only testing the variable, trying again and again until it succeeds, right? But which basically means it is not doing any productive work, any useful work. So you are wasting the resource, right? So that the other thread, thread 1, thread 2, thread 1 succeeds and gets the lock, it enters the critical section, thread 2 fails, and it will keep spinning here, right? So it's not, so when it is spinning here, so it basically means it is occupying the core, right? Because you need the code to execute this one statement. So you are wasting the resource. So what we can do is that we can actually, one option is that, okay, if we are fine with this, then we can keep this approach of spin lock. When we are fine with the spin lock or with this wastage of resource, when we know that the critical section of this thread 1 is small. If this critical section is small, after that it will set lock equal to 0, and then this one will able to continue, right? But let's say if this critical section is not small, let's say it consists of thousands of instructions, I don't know. Then we don't want to have this spin lock, right? So what we can do is that in that scenario, an alternative is, what we can do is that if the thread 2 fails to get the lock, we put it into the waiting queue. This thread, we put it in the waiting queue, and then we have some mechanism which informs the thread, all the threads which are waiting on this lock, which are in the waiting queue, which informs them that, okay, now the lock is released and move them into the ready. So which basically means that when we put them into the waiting queue, it will release the code. So since it will release the code, maybe another process or another thread which doesn't need the lock can proceed and use this lock, use this code for its own computation. So in this way, we are increasing the resource utilization. But what is the drawback? That we need the mechanism to move it in the waiting queue. Then we also need, and this is not only one thread, maybe there are multiple threads waiting on this lock. So all of them need to be moved to the waiting queue, and then all of them need to be notified when the lock becomes available, so that they are moved to the ready queue and they can test the lock again. Okay. So what we need at the minimum, what we need. So when it fails to get the lock, so we move it to the ready queue. And then when the lock becomes available, we move it to the waiting queue. And when the lock becomes available, we move it in the ready queue and then schedule it again. So at least there are two context switches from the perspective of this thread. Once when it is kicked out, and once when it is restored. So there are two context switches. So if this critical section, so let's say the time taken by those two context switches is let's say take time x. If the critical section of this thread 1 is smaller than the time taken by two context switches, then we say, okay, we are fine with the spin lock. But if the time taken by this critical section of the thread 1 is longer than the time taken by the two context switches, but then we say, okay, it is more performance efficient if we put it in the sleep, put it to the waiting queue, and then restore it when the lock is released. So basically, the idea is that if your critical section is really small, you can use the spin locks. But if your critical section is really long, avoid the spin locks. It is better to put the threads in the waiting state and then restore them when the lock becomes available. Any questions? Okay. Oh, we have done this. Okay, let me just read this one. So such a lock, which we have covered in the previous slides, such a lock is also called a spin lock because it keeps spinning. Since it is busy waiting, use of spin locks in uniprocess systems is very inefficient. So like there are also like two scenarios: multiprocessor system and uniprocessor. In uniprocessor system, it is more expensive as compared to multiprocessor, because in multiprocessor you at least have other cores where you can run your processes. But in a uniprocessor, you have only single core which you are occupying, and you are doing nothing useful. Use of spin locks in uniprocessor system is very inefficient. One process B will spin during the whole time quantum. Let's say it is given a time quantum of 10 time units, and in those 10 time units will just keep spinning. If the lock is held by another process A, which was kicked out, but it can be useful for short critical sections in multiprocessor systems. So kernel uses spin locks to protect short critical sections of few instructions on multiprocessor systems. But if it is long, then don't use them. So here is like just a graphical depiction of how things work from the perspective of the spin lock. Let's say you have process A and process B. Both are using the same lock. Process A, it successfully acquires the lock, so it enters its critical section. Process B then fails. Definitely, if it gets the lock, the process B fails to get the lock, so it will keep spinning. And as a result, it will be occupying this core, CPU, just to spin, just to execute the while statement all the time. And once it is done and releases the lock, then it will be able to proceed. But the problem is that then the CPU cannot be used by any other process. Maybe there are some other processes in the system which don't need the lock at all. Okay. So I think that's all for today, or not. Okay. So same thing which I have explained, it is possible to implement locks without busy waiting. There will be an associated waiting queue with the lock data type. A process that cannot acquire the lock will wait on the waiting queue of the lock. So when unlock is called on the lock, one of the waiting processes will be waken up and it will put to the ready queue. And that process will have the lock now. For now, we will not see how this is implemented, how we implement this mechanism. We are putting the thread to the waiting or the sleeping mode and then waking them up back. But we will see them in upcoming lectures. Okay. Any questions? No? Then that's it for now.